Now we look to the moving average process of order 1. Now we see that yt it is equal to mu plus et plus theta times et minus 1. Et it is just white noise with mean 0 and variance sigma square. We proceed to compute the moments. First, we compute the mean. That will be the expected value of the whole process. That is the expected value of mu plus et plus theta et minus 1. Since et is white noise, the expected value of this will be 0, and the expected value of this will be 0. So the expected value will be just the expected value of mu. Since mu it is a constant, it is equal to itself. So the expected value of yt will be just mu. Now we compute the variance. That is gamma 0. The variance, it is the expected value of yt minus mu squared. So it will be the expected value of et plus theta et minus 1, the whole stuff squared. That is the expected value of et squared plus theta squared et minus 1 squared plus 2 theta et minus 1. Now, we know that the white noise process is stationary, so it means that the variance will be sigma squared for all periods. So the expected value of this will be sigma squared. The expected value of this will be sigma squared. However, the white noise process is such that et is uncorrelated with its past values and its future values. So the expected value of the product of these two will be 0. So the variance will be just this whole stuff is gamma 0. Gamma 0, that is the variance, will be equal to sigma square plus theta square times sigma square. That is sigma squared times 1 plus theta square. Now we compute the autocovariances, and we'll start with gamma 1. That is the expected value of the product of this yt minus mu times yt minus 1 minus mu. That is the expected value of et plus theta et minus 1 times et minus 1 plus theta et minus 2. We must rely on the property of the white noise process. That is the fact that the residuals are of the that those ETs are uncorrelated with their past and future values. For this reason, we have to focus on the common elements of these two. The common elements are just et minus 1. For this reason, the expected value will be just the expected value of theta et minus 1 squared, that will be theta times sigma square. Then we look up on the general formula for the autocovariance. It will be the expected value of yt minus mu times yt minus j minus mu. That is equal to 0 for every j that is larger than 1, because we said that to be the autocovariance to be larger than 0, it requires common shocks, And when j is larger than 1, in this case, then there are no common shocks. Let's see it clearly. Yt is equal to mu plus et plus theta et minus 1, while yt minus 2 will be mu plus et minus 2 plus theta et minus 3. And we see that the shocks do not match. They do not match in no way. That is the reason why the autocovariances are equal to 0 whenever j it is larger than 1. Now that we have computed gamma 1 and gamma 2, we can compute rho 1, that is the autocorrelation function, that will be gamma 1 divided gamma 0. That will be theta times sigma square divided 1 plus sigma theta square times sigma square. That is just theta divided 1 plus theta square. In this way, it will not depend on sigma. Now we are concluded. Thank you.